We are done with the solubility of a gas in a liquid, and we talked about Henry's law and all of that. In this video, we will be discussing the two Intext questions given in page number 43. The first one, question 2.6. H2S, which stinks by the way, a toxic gas with rotten egg-like smell, is used for the qualitative analysis. If the solubility of H2S in water at STP is 0.195 molal, calculate the Henry's law constant. So they've given us certain important details in this question. First of all, the solubility is given as 0.195 molal. We've also been given the fact that it is at STP, which means standard temperature and pressure. So we know the pressure. And then we've been asked to calculate the value of KH. We need to calculate the Henry's law constant of H2S. Now, what we are going to do is, what does this mean? First of all, 0.195 molal. What does that mean? 0.195 molal means that 0.195 moles of H2S is dissolved in 1 kilogram of water. So 0.195 moles of H2S is in 1 kg of water. That is what we know. Now, this in turn means we have the number of moles of H2S, which is equal to 0.195. Next is the number of moles of water is equal to mass by molar mass. Now, at this point, I'm pretty sure you know molar mass of H2O is 18 grams per mole, and it is 1 kilogram of water, which means 1000 grams of water divided by 18 grams per mole. And this gives us the number of moles of water as 55.55. If you remember, we'd solved this for the the example question as well. So we have the number of moles of water, we have the number of moles of H2S. Now we can calculate what? The mole fraction. So the mole fraction of H2S equals to number of moles of H2S divided by number of moles of H2S plus number of moles of H2O. That is 0.195 divided by 0.195 plus 55.55. And this in turn, when you simplify it, you get it as 0.195 divided by 55.745, and that is equal to 0.00349, which can also be written as 0.0035. Last year, significant figure, sorry. Do remember that actually helps a lot. So you have the number of the mole fraction as 0.0035. Now, the next part is the problem part, I guess, because according to your textbook in class 11, you've been given that the pressure at the STP is 1 bar. That's what is given in your textbook, and that's what we are going to be following for this particular question. But if you think we should follow another value for the same, do let me know, and do let me know why we are doing it. Like, if there is going to be a modification, I will upload another video explaining the modification, I guess. But if you think there is a modification, do let me know. But from what I've understood and what I've read in your class 11 textbook from class 11 itself, that is in chapter 5, you've been told that STP, that is standard temperature and pressure at standard temperature and pressure, is 1 bar, and that is what we are going to assume. So pressure over here is equal to 1 bar. We have the mole fraction of H2S, that's 0.0035, and we know mole fraction, KH equals to pressure divided by mole fraction, because Mole fraction equals to kH into pressure. Using this equation, we get this. So substituting the values, you get 1 bar. And remember, your mole fraction does not have any units. So this gives us 285.71 bar. Again, if you think we should have substituted the pressure as something else, do let me know in the comments below. Or if you want, you can send me an email. The address is in the channel's description box. Or I think in the about section, I guess. Okay, the next question. Let's just go over what we did. We were given the solubility is 0.195 molal, which means 0.195 moles in 1 kilogram of water. Now from there we were able to calculate that the number of moles of H2S is going to be 0.195. So in 1 kilogram of water, what's the number of moles is what we calculated as 55.55 moles. After that, it was easy for us to get the mole fraction, and then we knew pressure is equal to 1 bar based on standard temperature and pressure, and we got the mole fraction, and we just had to substitute the values that we knew to get the Henry's law constant, that is KH. The next question, Henry's law constant for carbon dioxide and water is 1.67 into 10 to the power 8 pascals at 298 Kelvin. Calculate the quantity of carbon dioxide in 500 ml of soda water when packed under 2.5 atmosphere carbon dioxide pressure at 298 Kelvin. Now, first important thing that we need to notice is that the temperatures that have been given to us, 298 and 298, they match. So we can assume safely that the Henry's law constant, that is KH for carbon dioxide, is 1.67 into 10 to the power 8 Pascal. And we know that the pressure is 2.5 atmospheres. Okay, now what do we need to calculate? The quantity, the amount or the mass of carbon dioxide in a particular volume of soda water. Alright, so here we have, first of all, if you notice that KH is in Pascal and pressure is in atmosphere. Now when you look at this equation, the units of KH and Pascal, they get cancelled, or rather, they tend to be the same, I guess, and that in turn means that we do not have to worry about them. Okay, full disclosure, this is wrong. Basically, it's actually supposed to be P equals to KH into mole fraction. I'm really sorry. The reason I realized was because mole fraction has no units. The units of pressure and KH gets cancelled with each other, and that in turn gives us the unitless mole fraction. I'm really sorry that I wrote the equation incorrectly over here. So mistakes are normal. I would love to record another video of doing the whole thing all by myself, but I would like to show you that it's quite normal to make mistakes and we just gotta fix it. Okay, calculate the quantity of carbon dioxide and 500 ml of soda water. So we have the pressure and we have KH, and they both get cancelled. And because of that, we need them both in the same units. So we know that based on last year's knowledge, you should know that 1 atmosphere equals to 1.01325 into 10 to the power 5 pascals. So 1 will be equal to, so we want the atmosphere unit on the denominator. So 1.01325 into 10 to the power 5 Pascal divided by 1 atmosphere. So we'll be multiplying this with the same. So 2.5 atmosphere into 1.01325 into 10 to the power 5 Pascal divided by 1 atmosphere. This and this gets cancelled, and when you simplify this, you get 2.5331 into 10 to the power 5 Pascal. So we have that. Now, from the value of KH and P, we can calculate the mole fraction. So the mole fraction of carbon dioxide will be equal to this means this will go down. So pressure divided by kH. So let's substitute the values. That is 2.5331 into 10 to the power 5 Pascal divided by 1.67 into 10 to the power 8 Pascal. Pascal and Pascal gets cancelled, and when this gets simplified, we get 1.5168 into 10 to the power minus 3 as the mole fraction of carbon dioxide. Now, okay, we have the mole fraction. From the mole fraction, it is possible for us to calculate the number of moles of carbon dioxide, and that is what we're going to do. So what we are doing over here is we have been given the value of the Henry's law constant. We have been given the pressure. We are first calculating the mole fraction of carbon dioxide. We will then calculate the number of moles of carbon dioxide, and then in the end, from the number of moles, we can calculate the mass of carbon dioxide. So that is what we're going to do from now on. So we know the volume of water, which is going to assume it's water, is 500 ml, which means it is mass of water is going to be 500 grams. So remember, this 1 ml is always 1 gram based on the density calculations. So you have the number of, so you have the mass, you have the, the molar mass of water is 18 grams. So the number of moles of water is going to be 500 grams divided by 18 grams per mole. Grams and grams gets cancelled. We're left with moles. That is 27.78 moles. So we have the number of moles of water. We have the mole fraction. So we can find out the number of moles of carbon dioxide, because CO2 is equal to NCO2 divided by NCO2 plus NH2O. Now we're substituting the values that we know. So 1.5168 into 10 to the power minus 3 equals to NCO2, which we don't know, by NCO2 plus 27.78. So the next thing we do is we get this to this, we multiply. Okay, so that's NCO2 equals to NCO2 plus 27.78 into 1.5168 into 10 to the power minus 3. And basically, I'm going to simplify this. And this 10 to the power minus 3 is going to be taken, and like we're shifting the zeros so that it's easier for us to multiply stuff instead of dealing with the exponent. And we get NCO2, when we simplify it that way, we get 0.00152 NCO2 plus 0.0421. And basically, when we simplify this, that is, we'll be taking this to this side, and then we calculate the value of NCO2. That is 0.0420 is the value of NCO2. So we are able to calculate the number of moles. All I did was simplify this equation. And then we'll have to calculate the mass. We still need to calculate the mass, but we know the number of moles of carbon dioxide is 0.0420. We know the molar mass of carbon dioxide is how much? 44 grams per mole. Sorry. We know the number of moles. So mass of carbon dioxide equals to number of moles into the molar mass. So number of moles is 0.0420 into 44, and that gives us 1.85 grams. That's it. So when you look at this question, it seems like, oh, they've asked us a lot, but in reality, they just asked you how much is the quantity of carbon dioxide. So what we had was, we have the Henry's law constant, and we had the pressure, and from that we were able to calculate the mole fraction, and using the mole fraction we were able to calculate the number of moles of carbon dioxide. Because we know how to calculate the number of moles of water, from there we were able to calculate the number of moles of carbon dioxide, and then we calculated the mass of carbon dioxide using the molar mass as well. Once again, I'm really yeah, this is wrong. Remember, pressure equals to kh into mole fraction. And that's about it. With that, we're done with the Intext questions related to solubility of a gas in a liquid. In the next video, we will be discussing the applications of Henry's law.